Welcome to a new DoubleFox video tutorial. This is a demonstration of functionality related to GDS II layout files. GDS II is a very old file format started in the 1970s. The name GDS means Graphical Design Station. The file format contains commands like tape change and so on, showing that it originates in a time where big amounts of information was commonly stored on magnetic tapes. Despite its age, the GDS II format is still one of the mostly used formats when describing layouts for integrated circuits. It is a hierarchical format which allows describing polygons, which are then organized in arrays and grids, which then can also be reused and organized in arrays. This makes it possible to define a huge amount of polygons, but using only a comparably low amount of data. In this video, I show how to use it for navigation and how to create virtual images, which then are used for exact positioning and structure comparison. Like in the other videos, we use the Carl Zeiss Scanning Electron Microscope with a Gemini column for this demonstration. As a software interface, the DoubleFox own SEM control software is used. Now let's switch to the CorrMeas software. We start by opening a GDS file. We go to File and Load GDS Layout. Yeah, here it is. And now it opens. It takes some time to redraw this structure because it needs to filter out which polygons should be drawn. We see here different colors, and each color belongs to a certain layer. For the chip I use, this doesn't have the layer with the green color written on it, so I will disable it. Let us switch now to the SEM side. You see the sample is under the column. It's a small piece of a wafer, and it resembles approximately what you see in the GDS layout. Let us switch to the SEM, going to the in-lens detector. And yeah, you can see we have here some numbers and the same structures that you can see on the GDS layout as well. And you can see that this is more or less the same writing as we have here in this structure. So the first thing is now we need to align the coordinate system of the GDS file with the coordinate systems of the electron microscope stage. I have predefined some positions here, lower right. This is going to this number 29, and then having this feature here, I need to be sure that the beam shift is switched off. And I will go to this location here and by hand. I'm using the joystick right now, and I'm going in and make a good image so that we can also use the autofocusing functions by using plane shift. Okay, so this is now the right position. Approximately, the stage has a precision of about 3 micrometers, so I don't need to define it more precise. So let's go to the other side, and we have to locate the 29 here, and I will go to the same position, and we are approximately here. I create a new position like that and add it to the coordinate system. So this is our first reference point, and I go to the other software. We take the next point now, and this is similar. It's close to the number 9, and we go again to this position here, and I can do also some nice focusing on this position. Yeah, let's do the focusing. Yeah, like this is okay. Yeah, here is the number 9. Yeah. We exactly target the same location. I right-click at the reference position here, and I add this to our coordinate system. Now We have defined two coordinates, and we can already see that the structure jumped to the right location, and the red cross indicates the current state position. And if I overlay now the electron microscope image, you can see that this is aligned. And if I go to transparent mode, you can see that they are perfectly aligned on top of each other. If I move now the stage, you can see that with some precision, but you can see that the whole thing moves and follows my stage movement, and you can see how good this works. For the next point, I have one more point, and that is the upper left here. Yeah, okay. So that is the position 2. Okay, Y2. Let's take position 0. I don't remember why I used the 2, but let's take 0. You should always move your reference points as far away from each other as possible. So let's do some focusing. Reduced. Maybe I reduce the contrast a little, make it like this. I think this should be good enough. Now we are here. Beam shift is still 0. No, it's not exactly 0. Okay, but it's nearly 0. Then we go to the CorrMeas side and we go to the 0 position up here. And it's, of course, it's already close to it because we have aligned it with 2 points already, but we make one more here to get this more precise because the other two are quite close to each other. So after adding the third point, you see that we are exactly at the right position. And we can check now how it works when we, or how good we are with the precision. If I go to this number 13 here, right click, move stage here. And you can see we have some offset here now, and we can actually measure that. This is 4.8 micrometer. It's actually a little bit more than the stage precision should give, but this can also be depending on how good the things are written here on this on this structure. Maybe I try to add a force position. Let's see whether it can improve something. We move here and I go to this. Adding a force position will over-define the coordinate system, and then we have 1 point too much, but we can just try whether this helps in getting a good or a better average precision. So we are here going there, and okay, I just switch off this, and we need to add the point exactly here again. And I add this. You see it moved a little bit closer, and let's just go to this point here where we have checked the precision again and switch on the transparency. I zoom out a little. It got a little better, but not very much. Let us just check how our reference points are, the old ones. If I go to the first one, um, this aligns reasonably good, yeah, within the stage precision. The second one is also okay, and the third one, this is also okay, and the fourth one, yeah, this is also just okay. Yeah. So we can't improve this. So that is the precision we can reach. You can see you can overlay the electron microscope image. You can work with the structures. You see immediately the deviation. If we wanted to have more or less highest precision, maybe at this point here, and you are looking for some very small things, then you may want to increase the precision locally, because when you are here anyway, then this could be a good idea. Therefore, for this, we can actually use a table offset. we can actually move the whole stuff to the right position so that we have locally a perfect match. And now if we are looking for smaller structures, we can exactly hit the right area. The good thing is with this manual offset, you can delete it afterwards, and then you are back to the settings which you have from the basic alignment. So you can redo this at different positions to get maximum precision. This precision we reach here comes from different effects. Of course, the stage is one. For getting a higher precision, there is, of course, a possibility that one uses encoder stage. Zeiss electron microscope can be equipped with encoder stages, and they have a much better XY positioning capability. So for finding structures, this may improve the positioning quality a lot. Okay, as always in CorrMeas, you can now start acquiring images in an automated way. For example, if we want to capture images here, maybe these numbers, just as an example, we can create a position here and then create a position grid. And this has here three columns and 10 structures on top of each other. So we say x3 and y10. I know that the distance x is 1000 micrometer. We should actually give it a minus sign because I'm on the right side. The y distance is 508 micrometer, why ever this is defined like that. The good thing, you can directly measure this, take these coordinates from the GDS files. So if I add this now, I have created a point here on all the numbers. And a very straightforward thing now is to add this to a process list, then define some imaging recipe. Yeah, so if we are, let's go here to the center of the number and go to the SEM side. We want to create an image like this size, maybe, yeah, with the in-lens detector. This is okay. We have 20 kilovolt acceleration voltage, maybe something like 7. Now this will at least work. Maybe we can also use 6. Well, that's just for making it faster. Of course, it depends on the beam current and where you are with your table and so on. Right now, with this 20 kilovolt at 5 millimeter working distance, we get this speed. So let's define this here as imaging thing. And then if you have seen my other videos, you can use the state system. And we just define an image type. We say record here, demo image right now, okay. And then we can here use a script generator for creating a capture recipe, and we say just demo image. We want this and press OK. We just call it demo capture. Okay, now we have a new recipe. We have the 30 thing. We can select this recipe, demo capture, and this should now go to all places and capture, and then we can set up which scan rate 7. We can take scan rate 6 maybe or so. Yeah, this is a capture recipe, and when I press start, then it starts doing it. So where is it now? Right now it's here. And if we look at the SEM, we are here. And you can see it just captures the images. Can we can follow this here when we go to follow mode. This goes relatively fast. You can also see that there now is a shift sometimes larger or smaller between the GDS structure and the captured image. That depends on how good the stage has moved to the target location, and because it's not an encoder stage, we have a certain position deviation which comes from the mechanical relaxation on the stage. Let us look for some of things image like this 27. Let's look on that. We can just compare it with the GDS to see the transparency. And you can see here, for example, that we have acquired this with 3 micrometer deviation. That's actually within the specs of the stage. You can just check some more images here. Well, here it's approximately the same. We can check here in the center. Oh, maybe here it's a little more. If we measure from here to here, this is more. We don't know what is how precise is our chip made. Yeah, this depends on how this is created. No. And now it's nearly finished. You can see we are on the last. And if we go here, you can see we have a nice list of images of all the numbers, and they are more or less at the right position. Yeah. This worked quite nicely because the magnification we use here is just below 1000 times. So the little deviation of the stage, even if you see we have a slight jitter when scrolling here through the images, the stage deviation doesn't disturb us very much. Yeah. But in some cases, or in most cases, I would say, you want to precision with better accuracy. Yeah. And if we do this, we can just repeat this. Here, let us create a point here at this corner, at position here. Then a position grid, 3 times 10,000 and 508, like that. If we now want to image this, we have the capture recipe here. I used demo image. Then let us define a new or redefine this image, the demo image. I will go to this here and yeah, we are on this corner here, something like this. Yeah, and we want, maybe we go to 15K, yeah, like that. And have this here in the center. Good. The contrast brightness settings are okay. So let's go to here and update the demo image. Now let's start the capturing process. We are here now. And now you can also see this here in the SEM. We hit somewhere, but actually not at this place where we want to record the image. I can stop this here. Let us see if we scroll up. You see that they are totally shifted, and this makes no sense to do just positioning without having any reference on this high magnification. So what we do here now is we can use the system to create a virtual image from the GDS file and then use this virtually created image as a reference image and then make it go to the right location with very high precision. So how to do that? We we go back to the original point here, which was this here, like that. And we should choose now the field of view so large that the position shift of the state shouldn't disturb us. So we should go in the direction of 1000, maybe 800. I want to have a little bit of the number here. Okay, let's do that. So, and then we go to the CorrMeas. We have something called GDS ref, and this, if we look in this script, there's a command image where create GDS image. This creates a virtual image from the position where we are currently, and that can then be used for making a position correction. And we use the current magnification view for this we call it demo ref, like that. Okay, and now we have the demo ref, and this should correct the position, and then we have the state demo image, which then captures the image. So we could now just use here our demo capture thing and yeah, like that. We have the table move, we have the activate state. We can, when we want to do it visually here, just go to the state thing, and then we take this guy here and put it down here, like that. Now we have the demo ref, the demo image, and the grab. So first we correct the position by using beam shift, then we capture the image, and then we grab it. Quite straightforward. We copy this back to the recipe, we keep the name, override the current recipe. That's it. Let's try how this works. We just started here and maybe watch it from the SEM side. Now we have created the first image. It's doing a beam shift calculation. And now you can see we hit the corner very good. Now comes the next position. Here you can already see that we are not at the right location, but then it goes much closer to the area of interest. There's also a small shift always because we use a very large view, and depending on how the features are displayed there, we have some deviation. And when we go to the CorrMeas, you can see here my script actually creates two images. We have the virtual GDS file image and we have the real image, and you can see there's a shift in between, and we can also see the correlation, which has the single point here, and therefore we can always watch this. This is just a view that comes from the state. I have just added this that you can see a little bit better what happens here. Yeah. Okay. You can see it a little bit working now. Watching how this works. We follow this. And yeah, you can see that these images still have some jitter. But if we go to some of the location, like this here, we can activate the transparency and then see how large our deviation is. And now we can measure that. This is 500 nanometer now. So we have reduced by this single step beam shift correction, we have improved the precision from something like 3 micrometer deviation to 400 nanometer deviation. Yeah. We are finished now, and we can see that actually the last image actually is strange enough not in the center, where the others are actually quite okay, I would say. Yeah, the large image not. We can have a look why this happened there. Let's go just to this position, then switch to the SEM and see. Yeah. Okay, that's clear. We have so much debris lying around here that the position recognition cost was not as precise as usual because of this stuff lying around here. This was causing an additional deviation. So yeah, that shouldn't be confused or one would expect that, I would say. Let us check how far we can go further. So maybe we could try to introduce another step with precision. So let's see how precise can we actually get with this procedure. And we do this going to the SEM and choosing another magnification, for example, like this, or we can also 5000. Maybe we can just set it directly to 5000x, like that. So to activate another magnification step, we go to the state system again. And you remember the first ref state was this here. And there's now another state type which can be used for refining. This doesn't delete the beam shift, which the other one does at the beginning. So we create another one with a current magnification and then call this demo ref 2. Okay, so in our capture script, we can here go to the automator. We now need to insert this, so the demo ref 2 state can then should go down there. That's it. Now we have demo ref 2, and then the imaging magnification, and then capping the image. So that should be it. We replace the current recipe and just try it. Need to select all these positions, of course, from there to there, and then add it to the, oh no, this one's here we don't want. Yeah, we do it again like that and that. Add 30 items. Yeah, that's correct. And we just press start. Let's watch it on the SEM side. We have the first image, then comes the second image, and then another refine, and then comes the image which should be quite perfect centered. Next area, first step, next step, and this hits exactly. Yeah, that's how it should be. It has created two images. We should check the precision on this image, and then we should disable the display of that image, otherwise we can't. We will see the other image below, and you see there is nearly no deviation between this anymore. If we measure this, this is just 50 nanometer. So we hit with this two-step way, we hit now very precise. And that's very important if you want to find small structures. We are finished with a double refine procedure, and you can see that the left side of the two images, or the left column, has very high precision, and you can even see now that the center part is still at the same place, and the dimensions of this feature itself change. We have three different, if you just look at the right bar here, we have three different positions all over. So all the three probably have different end position. We can just check this here. So just for a first test, we disable this one, switch the transparency of this one down, and you can see that there is nearly no variation here. 72 nanometer, where it is very hard to express where the feature starts and where it ends, because here you can see this blue line starts actually where the bright pixel starts, so there's basically no deviation at all. So that's worked quite nicely, and then we can concentrate on some other feature one can do with GDS files, and that is comparing the acquired images to the original structure. And one way to do that is one can right click on the image. There's a new tool called image comparison, and you can here, when you open this dialog, you can select the source image and the reference image and compare both. And the easiest thing we can do is comparing this current image with each GDS reference image. And to compare these images, they can definitely differ by the detection mechanism. And depending on how you detect the image, if you just look in the SEM, we can of course detect this or acquire this image in inlets with the inlet detector. When we acquire this with a SE detector, we can still see the same shape, but the edges are of course different, and the grayscales and so on. So the most important thing to do is to convert this into an image which you can compare. And therefore, this feature here has an edge detection, and that is commonly what one can use there. So with edge detection, what it makes is it's more or less similar to the edge detection that we can do interactively here in the image filter. Yeah, so if we have this here, and then we can do a lateral pixel filter and then say, okay, we want to create a symmetric gradient. And this we can do interactively here, but the image comparison tool has this built in, so that we can just switch this on and off and have some fewer things to regulate. So if we want to make an edge detection, this normally needs to be normalized, then filtered, and first the edge filter and then also a pixel filter, a lateral, and this we can adjust with the sliders here. You see the normal image is somehow noisy. If you just increase the contrast and so on and make edge, then you get a very noisy image, and that makes no sense. So you commonly nearly always need to filter it like this, and then you get the nice lines. You can easily, of course, do this on the automatic GDS created image, because this is pixel wise perfect. So here it's just subtracting 2 pixels and you can get the edge. Here there can happen more, especially if we are in this area. You can see there are single pixel and then we have 2 lines here and so on. We should set the invertation switch so that we get as much contrast and as little noise here in the background. There's another filter which is called region finding, which allows to remove noise pixels. For example, it makes an edge detection and connects all regions and counts their sizes, or counts a pixel which belong to the region, and then you can just disable the small ones. If you have these two images, you can see they look quite alike. And now there is here on the right side this comparison function. If I press calculate, it it puts these two images on top of each other, making another correlation calculation, and you can set the size reduction size to this here and activate the apodization. The resulting image in the result both should basically stay on top of each other, and you can see that um, this action here matched more or less this area perfect. You can toggle between the two images here with this slider. So up here, the images are very alike, but down here, there are some differences. This can have two reasons. One is that the structure are, of course, not really written as they are defined. The other effect can be that the magnification of the microscope is a little mismatched, and we don't know what the reason for this is here. It could be that the image simply from coming from the SEM is a little too small. But anyway, what this is doing it takes the white pixels from the reference images and finds the closest white pixels of the source image. And it measures the length difference between those and then calculates the average. So we can get an average distance here between the targeted structure and the measured structure. And this correlation function calculates it. And in this case, this is a deviation of 18 nanometer or average distance of 2.3 pixels. And in order to compare structure with result and origin, this can now be converted into an evaluation script just by pressing this button here. And we can call it demo compare. Pressing OK, this has created now a new recipe. And let's have a short look at that new recipe. Demo compare is here. We edit it in the automator. You can see this is actually doing quite a lot. It makes individual steps that we have just set up by the slider. So it makes a lateral image filter, an edge filter, a normalization, and this for both images. And after these two images are created, it calculates the shift, and then it crops the area which overlaps from both images, and then it does a comparison here. It compares the two images, and the result is the deviation in micrometer. And this result is set to the column deviation. Now, you can do more evaluation steps here when changing the script, but that is the basic which comes from the selection in the dialog window. So we can execute this now just by the images are still all selected. And if I select this recipe, demo compare, and then press start, then it's running. And you can see it takes some time for each image to do something. And there comes now a value. There has appeared a new column deviation. And for each calculated image, it calculates the resulting deviation. Yeah. And we can later on check how good this calculation was, then find out are there real differences or is this coming from something else which we see it. We can let this run now, and then after it's finished, we can compare the results. Okay, this is finished now. We can sort after the deviation. And you can see here the best images are up here. This is more or less up there. Yeah. Then next one is here. Yeah. So the first ones, these ones are the best. And let's see where are the worst ones. We can go. This is here actually on the right side. They are worse than on the left side. Now we can have a look here on the image with the biggest deviation, and yeah, we can see one problem here. It didn't take all white pixels, and we should actually improve the edge thing. You can see if I move the slider too much to the right, then we get a lot of noise. So that I should really put it here. Maybe the imaging was not perfect, and maybe the focus was actually not perfect. One should redo it. But yeah, let's try to get it better. When we activate now the region finding here, we can get away with this noise in the background, and I think this should be still good enough. We can press calculate here. And now you can see the result is a little better. It's 39 nanometer now deviation, but you can also see that the structures here, especially down there, they are quite different. Therefore, there is a real deviation here in these parts of the image you can have there. Where at other places, like here in these corners, the images overlap very nicely. We can just override our recipe by this demo compare and let it run again to see whether the values change dramatically. Okay, let's press start. We are finished. It has calculated all the deviations again, and we can see we have on this item now, where is this? Still the first column. This is really a low deviation. And the next one here, this is the center row. And then, okay, we have here some with some debris, but that shouldn't disturb so much. And this one here is there. Okay, yeah. So this here is extremely good. Why is this so good? Let's have a look at it. And we do some calculation. Yeah. This really matches as good as it can be, because it's a line width caused by the filtering that causes now and the pixel nearly overlap, so that we have nearly no deviation between these. And let's check the counterpart on the worst. The worst calculation. Yeah. Okay, you can see here the images overlap here at this part quite good, but this, for example, here, there we have a quite strong deviation. They are all, if we compare the structures, they should have been a little wider, and also these here down here, there's a bigger difference between that. So that definitely has less precision than the other one. Okay, then let's take one in the middle. You can just see that the stripes here are wider, and they match much better the original structure. And also here we have less deviation. We have still a deviation from there to there, so that this line is okay. Also from here to there. And this line is also quite okay, but we have a deviation here at this position now. So there are real differences at this magnification level. So this comparison test can give some information how the structures written on the chip are deviating from the original structure.